In this session, we are going to discuss the topic of geometric optics. In this lecture, we'll be discussing the ray optics, how the light reflects and refracts, and how the light interacts with different lenses. These lecture slides are taken from the lectures by Wayne Anderson. In this lecture, we are going to address the following questions. How do the light reflect and refract while interacting with different objects? How do magnifying lenses work? How do lenses and mirrors form images? And finally, we shall use the concepts of geometric optics to understand the principles behind optical devices such as camera lenses. So firstly, let's see how we are able to see different objects. If we have an object in front of us, we are able to see that object because the sunlight falls on that object, reflects from that object and enters our eye. Now we'll see how reflection occurs at plane surface. For this, we'll consider a simplistic assumption that the object is a point. If the object is a single point, then the light falling on the object is scattered in all directions. And when such light ray enters our eye, then we are able to see the object. Now let's see how the image of this object is formed when it is placed in front of a plane mirror. Now this point object is placed on one side of the plane mirror, and since it's a point object, different light rays travel radially outward from this point, and those light rays hit the interface of the mirror and reflect back. Now the reflection at the mirror occurs in such a way that the angle of incidence is equal to angle of reflection. In that way, different light rays coming out from the point gets reflected at the plane mirror. Now, if some person sees the reflection of this object, then they see that the light rays coming from this object are coming in this direction. Now, if we extend these reflected light rays that the person is seeing backward, then they'll all converge at a single point. And this location is where the person will see the apparent reflection of this object, which is the image point. So this point acts as a virtual apparent source of reflected light rays. Now let's see how refraction occurs at plane surface. The main difference between reflection and refraction is that if we have a plane surface, the reflected light bounces back and propagates in the same direction as the interface. In case of refraction, the light ray gets transmitted through the object. Generally for reflection, the object has to be translucent or transparent. In case of refraction, if the light ray is incident on the glass slab in this direction, this is angle of incidence, which is the angle made by the incident ray with the normal. Whereas when the light ray transmits into the medium, which is refraction, this is the angle of refraction. Here, the relationship between the angle of incidence and angle of reflection is n1 sin theta I equal to n2 sin theta refraction, where n1 is the refractive index of air and then n2 is the refractive index of the glass slab that we are using here. So now if you see the example shown here where the object point is inside a medium with refractive index of Na, and a person is seeing the object from outside where the medium is air whose refractive index is Nb. It is given that Na is greater than Nb. That means due to the formula for refraction, if Na is greater than Nb, then theta A should be less than theta B. That means if we take normal here, then this is theta A and this is theta b. And as we can see here, when the light rays are traveling from higher refractive index to lower refractive index, they deflect away from the normal, where originally the light has to go in this direction, but it has deflected away from the normal. And these light rays enter into the eye of the person to see the object. Thus, the apparent image that the person sees appears to be at lower depth compared to its actual depth. This is because the apparent refracted rays appear to be converging at shallower angle because theta b is higher than theta a. Now let's see how an image is formed using a plane mirror. If we see in this illustration on the left side, we can see that the object is present at a distance of s from the mirror, and the person is standing on the same side of the mirror as the object. Now, if the person wants to see the reflection of the object in the mirror, then if we construct a line diagram, the light ray from the point source travel towards the mirror and gets reflected and enter the person's eye. If we extend the reflected rays just like before into the mirror, and if we extend any other reflected ray into the mirror, either this or we can consider one more, and if we extend it, they all converge at one point, and this point is where the image appears to be present. Now here the point to be noted is that all the reflected rays that we see here, either this or this or this, they don't pass through the image, but the image is formed at the intersection of the extended geometric lines from these reflected rays. So this kind of image is called a virtual image, since the reflected light rays don't actually pass through the image. Now let's see two different scenarios. In one scenario, the person is looking at the mirror by standing on the same side as the mirror to the object, just like before. And in this configuration, the person sees the image to be behind the mirror at the same distance as the object. The distance of the object from the mirror is denoted by S, and distance of the image from the mirror is denoted by S dash. It is to be noted that S is greater than 0 if the object is on the same side as the incoming light, and S dash is considered negative because the image is not on the same side as the outgoing light, basically because it is virtual image. Now let's see a different case where the object is on one side of the mirror, that is inside the mirror, and the person looking at it is on the other side of the mirror. Now incoming light ray from the object refracts at the surface of the mirror and then it reaches the person's eye. Since, as explained before, due to refraction from glass to air, that is higher refractive index to lower refractive index, the angle of refraction is higher. So the person sees the image at shallower depth. That means h dash is less than s if n is greater than n outside, and h dash is greater than s if n is less than n outside. Here n outside is refractive index of air, n is refractive index of the transparent material. Here we are assuming it to be glass. Thus n greater than n naught. Now even here, if we see, the object is on the same side of the mirror as the incoming beam, thus S is greater than 0. However, the image and the outgoing light are on different sides of the mirror. Thus S dash is less than 0. Now let's see the characteristics of the image from a plane mirror. Let's look at this line diagram. This is the mirror M dash, and this is the horizontal X dash connecting the bottom of the mirror, the center of the mirror, and the object. Now, let's assume that this is the height of the object y and the object is pq. Now the light rays travel from the object in this direction and they reflect back, and the light rays from the tip will also travel in this direction and reflect back like this. Now if we intersect two reflected beams, we get the location of the image. Now q dash p dash is a reflection or the image of the object pq. And if you see, the distance between PQ to the mirror is S, and distance between mirror to image is S dash, and S is equal to S dash in case of plane mirrors. Angle of incidence is same as angle of reflection, and because of symmetry, if we see the lateral magnification, which is equal to m equal to height of the image by height of the object, is 1 in case of plane mirrors. So for plane mirrors, we can say that the image is virtual because image is on the opposite side as that of the reflected rays. Image is erect because, as we can see, the orientation of PQ and P dash Q dash is pointing towards the same direction, thus the image is erect and it is of same size, that is magnification 1. Now let's see why the image is reversed. Here we can see the object, which is a hand, and the image is reflection of the hand. If we see in both object and image, for the image to be the reflection of the object, in both the cases the thumb has to point towards the mirror. As we can see, the PR is pointing towards inside, whereas P dash R dash is pointing towards outside. Thus, this is what we call as reversing of the image in a mirror. This can also be seen in this image where the hand is reversed and even the letters written on the text is also reversed. Now let's discuss how the image is formed if two mirrors are present. So let's consider a point object present at this location in between two mirrors. The mirrors are placed orthogonal to each other at 90 degrees. Now if we consider only one mirror, M1, with respect to the object, then we'll have the image formed here as we consider reflected rays and the extension of the reflected rays intersecting at this location. And if we consider only mirror 2, M2, and the object, then the image of this object is formed here with respect to mirror 2. As we construct ray diagram for the reflected rays, and those reflected rays will converge at this location where the image is there with respect to mirror 2. Let's consider the image with respect to mirror 1 as P1 dash and the object as P. So we are getting two different images when we are considering two individual mirrors. But when we combine these two mirrors, then something interesting happens. The image in the mirror 1 acts as an object with respect to mirror 2. That means if we consider the reflected rays which are apparently originating from image in mirror 1 and they get reflected on the surface of mirror 2, then if we extend these reflected rays from mirror 2 inside mirror 2, then they'll converge at point P3, which is image with respect to mirror 2 of the image inside mirror 1. If we do the same in opposite direction, where if we consider the image in mirror 2 to be the object with respect to mirror 1, and if we consider line diagram of reflected rays from this point, and if we extend these reflected rays, they converge at the same point. Thus, by addition of a mirror, we not only get the images with respect to each mirror, but the combination of mirrors will create extra images as well. Let's see how an image is formed with respect to a spherical mirror. Firstly, we'll consider point object. In case of spherical mirrors, there are two types. First type is concave mirror, where the reflective side is on the outer side. That means the center of curvature and outgoing light are on the same side. For this case, we consider the radius r to be positive. Whereas, if the reflective coating is on the inside of the spherical mirror, that means the outgoing light ray and the center of curvature are on the either side of the mirror, then r radius is considered negative. Here r is the radius of curvature. Now, let's see how an image is formed for a point object with respect to a concave spherical mirror. In case of concave spherical mirror, if object is placed on the optical axis of the mirror at a point P, let's consider a incident light going from the object towards the mirror. It intersects the mirror at point B. Now, if we draw a normal at point B, because of the geometry of the mirror, the normal passes through the center of curvature. And if we draw perpendicular which is tangent to the spherical mirror through point B, then we can assume that tangent to be similar to a plane mirror and the reflection of this incident light at point B to be similar to a plane mirror along this tangent. Thus we get a reflected beam from point B which intersects the optical axis at point P dash. This is the point where the image of the object P will be formed. Interestingly, as we can see, unlike before, the reflected ray is actually passing through the image. Thus, this image is a real image and it can be captured on a screen. Now, let's see the geometrical aspects of this reflection. Here, on the right side, we can see the schematic of the same, where P is your object, C is center of curvature, P dash is the image, P is the point of incidence, and V is the vertex of the mirror. And if we drop a perpendicular from point B onto the optical axis, the horizontal distance between that vertical and the vertex is delta, and the height of B from the optical axis is h. Now, in this construction, we find many different angles. Alpha, which is the angle subtended by the incident ray with the optical axis, beta, which is angle subtended by the reflected ray with the optical axis, phi, which is the angle subtended by the normal with respect to optical axis, and theta, which is angle of reflection and refraction with respect to the normal. Now, considering the geometry, this angle is alpha, and this whole angle from the normal to the horizontal is phi. Thus, we get alpha plus theta equal to phi. Similarly, we get beta equal to phi plus theta. Eliminating theta from these equations, we get alpha plus beta equal to 2 phi. Now, let's see, we have three right angle triangles here. The three right angle triangles are PBO, CBO, and P-BO. Then, tan of alpha is equal to BO divided by PO, which is h by distance of the object from O, that is S minus delta. Similarly, tan beta is equal to h divided by PV minus delta, which is h dash minus delta. Similarly, tan phi is equal to h by the radius minus delta, as shown here. Now, we take an approximation called paraxial approximation, where assuming the small values for alpha, beta, and phi, that is alpha, beta, and phi tend to 0, and delta is far less than s, s dash, and r. Then these relations transform into alpha equal to h by s, beta equal to h by s dash, and phi equal to h by r. Substituting these simplified relations into alpha plus beta equal to 2 phi, we get this relation, which gives relationship between s and s dash, that is distance of object and image. Thus, we obtain object image relationship for spherical mirror, which is s1 by s plus 1 by s dash equal to 2 by r. Now, let's see the concepts of focal plane, focal point, and focal length. In a concave mirror, let's assume parallel beams are incident on this concave mirror. That means the object is at infinity. That means s equal to infinity. Then if we substitute s as infinity, in 1 by s plus 1 by s dash equal to 1 by 2 by r, where s tends to infinity, then s dash is obtained to be r by 2. That means all these rays reflect on the mirror and converge on a single point, which is at a distance of r by 2. This point where all the parallel beams intersect is known as focal point, and the distance between the focal point and the vertex is focal length, which is equal to r by 2. Thus, the focal length is half of the mirror's radius of curvature, which is f equal to r by 2. Thus, as explained before, if we have parallel beams incident on the spherical mirror, the object is at infinity, so S is at infinity. Thus, these rays converge at a point called focal point, which is at a distance of r by 2 from the vertex. Conversely, if we have an object at the focal point, then all the light rays that travel outward from the focal point gets reflected and gets converted into parallel light beams, implying the image is at focal point, that is S dash is at infinity. Thus, substituting f equal to r by 2 in the image object relationship, we get this relation, which is 1 by s plus 1 by s dash equal to 1 by f. Now, let's see the case where the object has a finite length. So far, we have only seen the object, a point object, which doesn't have any lateral dimension. However, if we consider an object with lateral dimension, that is image of an extended object, then we get another factor called magnification, where the lateral length or lateral dimension of the object can be magnified or diminished. So let's assume the object to be PQ, where P is the point on the optical axis of the concave mirror and PQ is the height of our object. Q is the topmost point of our object. Considering two incident beams from the object, the light ray that is incident on the mirror at the vertex gets reflected back at the same angle theta below the optical axis, whereas the light ray that passes through the center retraces the same path after reflection because of the geometry of the sphere. Thus, the point of intersection of these two light rays occurs at point Q dash, and thus P dash Q dash is our image of our object PQ. It is interesting to know that the distance of the image S dash is less than S, as we can see here. At the same time, because of this, since theta is same geometrically, the height of the image, which is y dash, is found to be less than y, that is height of the object. Thus, our magnification, which is height of the image by height of the object, is less than 1. That means the height of our image is diminished with respect to our object when our object is placed beyond the center of curvature of a concave mirror. It is important to note here that when we say m less than 1, it is just that the magnitude of m magnification is less than 1. That is, the magnitude of the image size is less than the magnitude of the object size. However, in actuality, here we have to consider y dash as negative because it is in the opposite direction. Thus, y dash by y is, that is, y dash by y is actually in between -1 and 0. That means m is less than 0. That means the object is inverted. Now let's see how an image is formed if it is a convex mirror. In case of convex mirror, when a point object is placed along the optical axis at a distance s, assuming two light rays, one along the optical axis which retraces back as it reflects and another gets reflected at a point B on the spherical mirror. Assuming the tangential line at point B to be similar to a plane mirror and using the laws of reflection, we get reflected ray. Now extending this reflected ray back, extending both the reflected rays back, both of them intersect at point P dash, which is where the image is formed. Since the reflected rays are not passing through the image, it is a virtual image. Now looking at the geometry of the ray diagram, we have the angle alpha, which is angle subtended by the incident ray with respect to optical axis, angle beta, which is angle subtended by the reflected ray with respect to optical axis, and angle phi, which is angle subtended by the normal at the point of incidence which passes through the center of curvature. And phi is the angle between this normal and optical axis. Since the center of curvature and outgoing ray are on opposite sides of the mirror, R is considered negative in this case. Similarly, if we construct a line diagram for an object with finite length PQ equal to y, we get an image Q dash P dash with height y dash. Here, as we can see, y dash is less than y. That means for convex mirror specifically, we can see that both the object and the image are pointing in the same direction. That means the image is erect and the image is not inverted as we have seen in the concave mirror. Thus, m equal to y dash by y is greater than 0, which corresponds to erect image, and the magnitude of m is less than 0 because the size of the image is less than the size of the object. Thus, the actual value of m is y dash by y lies between -1 less than m less than 0. This also satisfies with the ratio of m equal to minus h dash by s, where here, since the outgoing ray and the image are on opposite directions of the mirror, h dash is negative. So we substitute h dash less than 0, then m becomes positive. Similar to concave mirror, if we consider focal point and focal length for convex mirror, doing the same exercise as before where we assume parallel beams hitting the convex mirror, that is h tends to infinity, then all these rays gets reflected and diverge. However, if we extend these reflected rays inside the mirror, they all intersect at focal point f, which can be obtained from the object image relationship, which is 1 by h dash plus 1 by s equal to 2 by r, where when h tends to infinity, h dash tends to r by 2. This slide shows the different concepts that we have discussed so far regarding the ray optics and graphical methods used in it to obtain the location of the image corresponding to an object in case of a spherical mirror. Both these figures show the formation of an image corresponding to an object when the object has a finite length. Schematic on the left hand side shows the reflection of a finite length object using a concave mirror, whereas the schematic on the right side shows the reflection of a finite length object using a convex mirror. This slide shows how image is formed when an object with a finite length is placed at different distances along the optical axis of a concave spherical mirror. When the object is placed beyond the center of curvature, then image is formed in between the center of curvature and the focal point. Here, the image is inverted real and the size of the image is diminished. That means the magnification is less than 1. Now, when we move the object to the center of curvature as shown here, then the image is formed at the same location, that is center of curvature, having the same size but inverted. Here the image is real and the magnification is 1. When we move this object in between the center of curvature and focal point, the converse of this case happens, where the image is formed beyond the center of curvature, which is inverted but real. Here the magnification is greater than 1 as the image is enlarged. Now, when we move the object to the focal point, then all the light rays emanating from the object are converted into parallel beams. Thus, they won't intersect to form an image. Thus, the image is formed at infinity when the object is placed at focal distance. Now, when we move the object further closer to the mirror, even closer than the focal length, then a virtual image is formed behind the mirror.